So for the biomechanics lab, you've been asked to fit your stress relaxation data to these two different models of viscoelasticity. So we talked about these two different models, and now you've got this raw data from the test frames. So first step is you need to prepare the data to go into MATLAB. So the equations are in the format of stress and time. So we need to get the appropriate stress and time. So you have to do some calculations based on the cross-sectional area of the skin to calculate stress from the recorded load. My recommendation is to use Excel to prepare the data, so I'm just going to provide you some tips just as a refresher if you don't remember from first year engineering. So you've got hundreds if not thousands of pieces of data, so you don't want to make a calculation for every single point. So to copy a function you've entered, mouse over the bottom right hand corner and drag the cells to all the cells in the column. Since I'm making a calculation based on the area I put in cell I4, I want to make sure that I4 is static by adding a $sign before I and before 4. That way Excel knows to hold the value constant in all the calculations. So you can just drag and update all the calculations again. If you want to preview the data in Excel by making a graph, that can be a nice addition to your lab notebook. Just make sure you've edited the graph so that it has a meaningful title and the axes are labeled with appropriate units. So in a minute you can see in the graph that the data was collected for the first and second segment of the test, but for fitting the parameters in MATLAB, we only want the portion of data that occurs right when the material reached the full extension. So at the point where it actually has the peak stress. So in my case, I know that the skin was extended 10 millimeters. So I'm going to edit the data so that the time begins at 3 seconds. This is also that just happens to be the same point when the skin has reached 10 millimeters and is at full extension. So then I'm going to use this new time data and the calculated stress data to fit the parameters in MATLAB. So I'm just going to copy and paste those, and in MATLAB I'm going to create the two variables that we measured in our mechanical test, the time and stress. So I'm just copying those from Excel like I showed you, and I like to create each variable separately as a vector. So you can do this by hitting new variable, and then I just copied and pasted from Excel, so I'm just deleting one of the columns and leaving stress. And then I'll do the same exact thing for a new variable for time. So you can see in the lower right-hand corner that I have a variable, that both variables are actually 972 data points long. So they're the same exact length, so they're matched with each other. That's important to check. So next I'm going to open curve fitting in the apps tab of MATLAB. If you can't find this, then you need to install the app. You can do that by clicking on the icon in the top left-hand side, get more apps and install app. You'll need to define which variables are the X data and the Y data. You should get a pretty similar graph to what we saw previewed in Excel. So what we want to do is fit the data to estimate unknown parameters in the viscoelastic models with our known parameters of stress and time. So I'm starting off by fitting the data to equation 1 of your post lab. You'll have to do this with both equations. So it's an engineer's rite of passage to have to enter complex equations to get all the parentheses correct. So you're not going to get the right fit right off the bat. So there's a few things that you need to try to play around with. So in this case, I did get a pretty decent fit right off the bat, but that doesn't always happen. So on the left-hand side is the results, which tells me the estimated values for the 4 unknown parameters of this equation. It also gives statistics on goodness of fit. So 0.92 is pretty decent for the R-squared value. One thing that reliably improves your fit, if it isn't already the best, is by editing the lower bounds. So to do this, you want to click on the fit options, and when this window opens, it almost never shows up right for me. So it's a little secret. You can drag and expand this window to show the boundary conditions. So it definitely makes sense for us to be making sure that all of our parameters are above 0. So you want to change those from -infinity to 0. At this point, we pretty much have everything we need to analyze equation 1, although I highly recommend you edit your graph to include a title and axes with units. So you can do this in File, Print to Figure. And in this window, you can change all sorts of things. But I'm more concerned with editing the title to make it a meaningful title. And also you'll want to edit the axes so that the axes include units, because the default is just to have the labels of your variables. So for other things to think about for your lab report, you want to make sure that you have at least a screenshot of the coefficient estimates with the fits of the unknown parameters for both equations, and also include the goodness of fit. You also want the edited plot with your data and the fitted model for each. You can also save your plot as a figure by going to File and Save As. So just change the option to something like a JPEG so that it goes into your lab notebook nicely. So spoiler alert, one of these two models will fit your data much better than the other. So just a refresher, when interpreting this data, you want to decide which model fits the data better. So for the equation 1, there's one set of time constants. The time constants tell you a rate of relaxation. So the larger the time constant, the slower the rate of relaxation, which means the material will behave more like a solid rather than a fluid. In the second model, you have two sets of relaxation coefficients. So one set mathematically describes the initial relaxation rate, and the other describes a slower relaxation rate. So this describes a composite material that has components that relax at different rates. So hopefully this helps in your post labs, and good luck with MATLAB and have fun doing analyses.